So we have a bit of a smaller section today, but that is perfectly fine. Yeah, so we are going into our last discussion sheet on network security. We've just wrapped up with, I believe it was denial of service as well as firewalls. But our first question on the discussion sheet is actually going back to one last thing that we didn't cover last time about DNS. So I did want to give a brief review of NSEC and what it is. It's an extension, or no, it's not an extension. It's a part of DNSSEC because we have signed records saying that these domains do exist, but it's harder for us to be able to authoritatively, sorry, that's the word, authoritatively say that this domain doesn't exist because we can't somehow, predict that someone's going to ask for, pretend.domain.cs161.org. So we can't generate like this domain doesn't exist as a signature ahead of time. So what NSEC does is we actually assign responses saying two adjacent domains in alphabetical order are, for example, oh.cs161.org and project3.cs161.org. And that implies that there are no domains that exist between these two domains. And so if we receive a request to pretend.domain that is between those, then we can just send back that NSEC response. And that is how, and the client can verify the signature on this and thus like prove to itself that pretend domain doesn't actually exist. Side note, these two domains actually do exist. You'll use project3.cs161.org for project 3. That was all I had for the first question. So the first question, it's just generally talking about NSEC. It's talking about some vulnerabilities that I think were covered in lecture, and we're actually going to construct a different way that avoids one of the more prominent vulnerabilities in standard NSEC. So yeah. Yeah, do you just want to read through the question and then we can talk about it?
Okay.
Sure. Yeah, feel free to just say whatever on your own time.
For part A, is it just if they manage to poison the DNS cache? Like you need the signature to verify that it's actually from the server and not from some adversary.
So this question is actually asking like, non-existent domains don't really, it's not like the same kind of damage as if I managed to spoof a record saying this domain is at this IP address. So it's really asking like what becomes possible if there's no way to verify whether this non-existent domain response is valid or not. What could the attacker do?
They could just repeat the non-existent thing and then create denial of service.
Right, denial of service. So let's say someone makes a request to google.com. And if I, as the adversary, manage to beat the name server in sending back, oh, google.com doesn't exist, and the client has no way of verifying that, that becomes a denial of service. So yes, that is exactly correct. Let me actually switch to my iPad here first. Also, completely unimportant side note. I don't know what happens, but this turned from Perrin and Ryan into Cow and Lemkill. So that'll be fun when they find out. So yeah, this becomes basically denial service for domains. I'll turn this blue because why not? So the second question is asking, yeah, why don't we just sign every, why don't we just sign every non-existent domain response? If someone asks for, non-existent.161.org, why can't we just sign a non-existent.161.org domain doesn't exist and just send that back?
Is that to do with like how in order to do that you would have to do it on the fly and not like have like a pre-generated signature because you can't predict what they could request?
So what kind of vulnerabilities would this introduce?
So if an attacker wants to overwhelm the website, then they could just have a bunch of random strings to that domain, and then your server would then have to process through a lot of those.
Yeah, exactly. So force lots of signatures. And we talked about before how asymmetric cryptography is generally a lot more computationally intensive. So this would, overwhelm the server. Can you also think of, what would happen if the server gets compromised? What might the attacker be able to learn?
All the valid domains.
Well, in order to compute these signatures, what does the server need to have in memory, or what does it need to store on the server if it wants to compute signatures on the fly?
It needs the key to.
Yeah. Do we need that when we're, pre-computing the signatures and just giving the signatures to the server?
No.
Right. So what would an attacker learn if they manage to compromise the server?
The key.
Yeah. So attacker or compromise of the server might lead to compromise of the key, and then the attacker could now sign their own DNSSEC responses. Compromise. Right, okay. So, yeah, using the original DNSSEC protocol, how could an attacker somehow learn every domain that exists on this, subdomain?
So the original one was the one in part A, right?
Yeah, so this is just the standard NSEC, which I was talking about on these slides. It just, yeah.
You could just make a lot of different strings that spans, like you can query a lot of different strings, and then that will give you back a pair of valid domain names, and then you can keep doing that to learn.
Sure. Okay. So let's devise maybe not an algorithm, but just some sort of protocol for this attack. So what would be maybe the first domain you would try to query?
You could start at the very beginning. So you could do a.google.com.
Yeah, sure. Let's do a.google.com. And what will the name server return?
The A1 thing, right?
Right. You'll get like an NSEC. And then let's say, actually, I forget how NSEC works when it's like before the first one. I don't remember off the top of my head. But let's just say from this NSEC response, you learn that there's, docs. I don't know why I keep switching handwriting. Google.com. So what would be the next domain you would query in this case?
Something off the docs. So you could do, I know, like the Z.
Sure.
Or something like that.
Or you could probably even do like docs A or something. Just, so you make sure you're right after docs. So docsa.google.com. And then you would get back something like NSEC, which is between docs and, let's say you learn, I don't know, drive.google.com, and so on and so forth. So this is really just, I guess we call it an enumeration attack. It allows an attacker to learn all the domain names, and sometimes you might not want this. So, what this next question is asking is, how could we maybe design a like an addition, or not an addition, a alternate version of NSEC that allows us to still verify that a domain doesn't exist, prove that it doesn't exist, but without allowing this domain enumeration.
So they could just hash the domain you're requesting,
Okay.
and then they can then just look up if they have like a table of valid hashes.
Mm-hmm.
And because hashes are one way, they could just reply with an NSEC of the hashed
Okay.
domains.
So what would this new NSEC response contain? Let's say docs.google.com hashes to bf63, drive hashes to a372, and let's say mail hashes to 0, 1, D5. I don't know, just making up numbers here. So what would an example, first, what would you construct these NSEC records as, or these new NSEC records as?
Would you just give them the hash?
Okay, so how would you sort these hashes?
Um, I guess alphabetically,
By the original name or by the hash?
the hash.
Right. I'm just coming up with more numbers here. C6, sure. So yeah, so we'll say, okay, so there's no hash or 0316C to A372 to BF63. So let's say we get a request to non-existent. How would you figure out what record that we need to send back?
You could hash the non-existent.
Okay. Let's say this becomes 57AB. So what would you send back in this case?
The 31C6 and the A372.
Exactly. Yeah. So essentially what this does is we're sending back this NSEC3. Spoilers, this thing exists and is called NSEC3. We're saying that, okay, there's no domain that hashes to a hash that's between 3.1 and A3. So this implies that this hash must have come from a non-existent domain. Does that make sense?
Mm-hmm.
Yeah. So like I mentioned, this protocol is called NSEC3. It's actually, I think, what's used most commonly nowadays in DNSSEC. But
is it still vulnerable to a dictionary attack? Like if the attacker really wanted to find out.
I will highlight this down here. You're touching. You're getting at a very good point. But I guess for E, how would you answer this? How does it prevent enumeration attacks?
So this prevents it because now all the attacker gets back is the hash and not domain name, and because it's one way, it's should be impossible for them to find out the original.
So you can only enumerate hashes, and thus because hashes are one way, it implies that you can't get back the domain names. Right. Now you touched on a very good point there. If an adversary has access to a dictionary that can, say reverse some simple domain names, how would you change this earlier enumeration tech to work this?
So you would still generate the the domain name, but then you would save into the dictionary like the domain name and the hash of that domain name, and then when you get back the result, you can just look up in your dictionary to see whether you have something that matches.
So we still need to start with some random, you might want to look up in your dictionary some hash that starts with, or that maybe starts with a bunch of zeros. And then so you send that domain, let's just say it's like, I don't know, XF or something. You send that domain and then you get back nsec3 and you get back between, let's say earlier we had 0, 1D5 and 3, 1C6. And what did you say we would do with these two hashes?
Sorry.
Oh, I think it's taking a while to update. But yeah, say we got back these two hashes, we would do what?
You can then look through 1C6 and 01DS in your hash table, or like just your dictionary, and then see if that.
Yeah, so you reverse this with your dictionary. And then you would just keep doing this, keep querying domain names, and you get back new hashes that you can reverse with your dictionary. This question asks what conditions must hold true for the domain names. I think it's a bit of an oddly worded question, but essentially what this is saying is that the domain names have to be in the dictionary. So if, say, actually I think Berkeley has some pretty obscure domain names sometimes, and especially like if the domain names are long and random, then they probably won't exist in the dictionary. So this is definitely still more robust than before, but it's still vulnerable, especially to like larger services who have tons of domains and they're probably simple like docs or drive or mail. I believe there's also an NSEC5. I don't know why they skipped the even numbers, first of all, but I think there's an NSEC5 which I haven't read into, but it's meant to prevent enumeration altogether and allow for like some sort of online signing that's safe. But I'm not too sure about that, but that's just background information that there's more in the works. So the second question is talking about denial of service. I just wanted to very briefly go over the couple types of DOS that we've talked about before we proceed. But denial of service is essentially trying to break this concept in security that we call availability, which I realize I've used the word available to define availability, but it's ensuring that a service essentially remains up, that if I as a user can still access a service even if an attacker doesn't want me to. DOS attacks attempt to break this availability, and there are a ton of ways to mount a DOS attack. Some of them are very hard to defend against. I know a lot of the ones that we've talked about in lecture have been network attacks, but we also talked about, say, if you share space on a server, you could consume the resources of that server, or there's just, you could make, I believe he also talked about making a SQL query that takes a long time to execute, which causes the database for a website to become overloaded. So there are many ways you can do this. In general, it's just to break availability. But this is probably the most standard DOS attack. If anyone has ever said that they were going to, DOS you, so to speak, this is probably what they're talking about. And it's essentially, this attacker is sending as much traffic to this, I guess, target as they can. And so this is very simple. It's just kind of one entity sending traffic to another. And if if the attacker's network connection is faster than the target's network connection, then their network gets saturated and they can't really access the internet. So this is the most simple kind of attack. The most, I think, common one is the distributed denial of service attack. It's abbreviated as DDoS. And this is essentially the attacker has control over multiple computers, probably on multiple networks, and they will all send traffic towards this one target. So even if, say, each individual computer only has maybe a megabit of bandwidth, and this has maybe 10 megs, if you have a ton of computers all sending 1 megabit, you're going to overwhelm the 10 megabits for the target. So this is a DDoS. It's very, you know, it happens in the real world. I believe in the real world, we get up to like gigabit or terabit denial of service attacks. So that's quite rough. More lately, we've also seen amplified denial of service attacks. So this is essentially, if I can find a way to only send a small amount of traffic to some server, and that server will send a lot of traffic, supposedly back to me, then I can use it to force the server to send a ton of traffic to my target. So the example Professor Wagner used was DNS, since DNS requests tend to be quite small, but if you have, the responses for DNS can get quite large, especially, with NSEC and whatnot. So essentially what the attacker does is it spoofs a packet to the DNS server, and then that packet will send a response thinking it's sending it back to, the person, thinking it's sending it back to the attacker, but it's really sending it to the target. And say if I'm sending 10 megabits in, this might get amplified to 100 megabits going to the target server. And usually these amplification vectors, usually like DNS servers and whatnot, have really large internet connections since they're handling so many requests. So usually this is enough to overwhelm the target. And of course, you can combine these. We've seen amplified distributed denial of service attacks. At this point, is just kind of a bad time for this target. In general, there's not much of a great way to defend against these network level attacks. But in general, we want to be able to identify different users so we can tell them apart. And then after we identify each user, we find ways so that they don't interfere with one another. So for something like sharing space on a server, that's making sure each user only has a certain, can only use so much computing resources, or you can only execute this expensive SQL query as a logged in user, and then you track that user can't execute it more than, I don't know, once every couple of minutes. Just stuff along those lines. And honestly, the most common way to solve this problem is just to throw money at the problem. So you just pay more for more resources so that there's a lesser chance that the attacker is able to overwhelm your resources. Throwing money at the problem. So that's all I had. We can go back to the discussion sheet. Sure, I can. My screen sharing. Can you see my screen?
No.
Interesting. Let's try this again. There we go. I think. Maybe not.
It just says you started
Yeah, I see that
screen
too.
sharing, but it's a black screen.
I think Zoom is being finicky. Let's try this again. Can you see it now? Okay, yes, I think so.
Yeah.
Okay. So this is just kind of giving you a scenario. We've got two servers, somewhere out on the internet. There's one that's charge n, I think, and echo. So actually, I'll just let you read through the question because I'll just let you read through the question.
It should be possible.
Okay.
So to perform a denial of service on Echo, you want to send the packet to port 7, right? Where the packet has like a large amount of data.
You're sending it to the Echo server? Because we've got two servers here. Yeah.
So if you want to attack address A, then you just have to make sure the packet arrives on 19, and then potentially the charge N could then send like a big packet back, right?
So it'll send back a packet with 0 to 512 characters. So it's, anywhere from very few to a little bit over 512 bytes if you include the headers and whatnot.
Mm-hmm.
And what this question is asking is how could we somehow make it so that both servers will, consume a lot of bandwidth. So we somehow need these servers to, we're only sending a single packet, but we somehow want to affect both of these servers.
Mm-hmm.
And you might want to pay attention to the fact that this is UDP.
Is it possible? Actually, wait. I don't think it's possible for Echo. So it's not possible to make address, like construct a denial of service attack on address B.
Okay.
Because address B only supports Echo, and Echo will only send back a packet with the same content. And since we're only doing it with no content, then it won't use up that much bandwidth. Like there won't be any amplification through Echo.
Okay. So is your idea that we want to, send a packet to Echo, and then this Echo will echo the packet back to us? Sorry, I'm trying to draw, but I think my iPad is being really
sorry, I didn't quite hear
unresponsive
you.
right now.
My audio kind of cut out.
Okay, can you hear me now?
Yeah.
Okay. So is your idea kind of just that as Mallory will send a single packet to Echo, and Echo will just echo it back to us?
Yeah, or if we spoof it from address B, then it will just send an empty packet to address B.
Actually, I think... Okay, so A is charge-in, let's just clarify, and B is Echo. So you're saying we spoof this packet. That means we're spoofing the source of the destination.
We want to spoof the source,
right?
I think.
Right, because Echo will then send a packet back to where it sees this. Echo will send a packet back to the source. So from who would we want to make it seem as though the packet is coming from?
Wait, sorry, what did you say? Sorry, Pat.
Because if we're sorry, no worries. If we're spoofing a packet, we're making it seem as though it came from somewhere else. So who would we want to put down as the spoofed source?
Oh, could we put it so that it seems like it's coming from the other server?
Sure. Okay.
Like
so
charge N.
We can try that. So Mallory sends this packet, and then Echo will echo that packet back to this charge-in server. So we need to, okay, so we say it's going back to the charge-in server. Is there a particular port is there a particular source port we might want to put down?
Yeah, we want to put the source port to be 19
Okay.
with address A, like IP address A for the source
Okay.
IP, and
Right.
then destination would be IP address B with port 7.
Right. Okay. So what happens after Chargen receives this packet at port 19?
Then it will reply to echo with some random number of bytes, and then echo will echo that back.
Right. So
and
this is
then
going to,
that will create, a chain.
yeah, so this will just keep sending data back and forth, and you can see how this quickly becomes messy and may start overwhelming. In reality, really what this might look like is you've just got one UDP packet bouncing back and forth. But if the servers are close enough, they're going to be sending that one packet really frequently back and forth with each other. So it might, build up over time. And Mallory, as an attacker, could always, send a ton of these packets so that there's a ton of packets just bouncing back and forth. But does that make sense what the attack looks like?
Hello? Wait, it's frozen.
Oh, can you hear me?
Yes.
Okay. Yeah, sorry. I think it's my internet. I'm actually not sure. So you said for the source IP, we will put A, and for the source port, we put 19. So we're pretending that it's coming from the server here. And then the destination, we need to actually make sure it's correct. So we send this to source IP B on port 7. And could we switch these two around? Would it still work? Oh, my internet connection is unstable.
Hello?
Sorry, I didn't quite catch that.
Are we on the second part?
Oh, I was just asking, like, could we switch the source and the destination? So we start by sending our first packet to charge N. Would that still work?
Yeah, yes. Because as long as we spoof it from echo, then that will also do the same thing.
Right. Okay, just wanted to make sure that was clear. So now the second part says, now assume we're using TCP. And it will only send back this response when you complete the three-way handshake. So could we execute the same attack in this case?
We'd have to guess the sequence number, right?
So is Mallory able
to do a?
Oh, go ahead.
So I don't think it's possible because after you send the SYN packet, then it will respond to the other server with the SYNAC packet with the new sequence number, which we won't know.
Let me draw this out here. I'm not sure how quickly it will update on the screen. So we're saying Mallory sends in this SYN packet. SYN, and let's say sequence number equals X. And then this will send a SYNAC to the other server. So SYNAC with ACK equals X plus 1 and a sequence number. Let's say it's Y. What happens when this server receives this SYN-ACK packet?
It'll probably just terminate the connection because it knows it didn't send the original SYN packet.
Exactly. It didn't send that SYN, so the SYN-ACK must be because of either some error or because someone was trying to spoof. So this server will immediately send a reset packet. And then you'll never actually get this data to, you'll never get this packet bouncing back and forth from each other. So in this case, no, because no blind spoofing. With TCP. Does this all make sense? Did you have any questions?
Yeah. No.
Okay. Yeah, it's a bit of a shorter discussion sheet today, so if you, unless you had any other questions, that is really all I have for you.
I had a question. So like when we query the DNS server, like the key that they sign it with will be, like the first one will be hard coded into the machine to prevent from tampering, right?
When you say the
Or like
first one,
like, so normally when we query the DNS server, it goes to the local one, right?
Right.
And
so
then if it's not in there,
yeah, so we query the local name server, and then
after that it goes to like the root and then the other stuff. And then I just wasn't, could you go over again like how they ensure it's like the responses is like has integrity?
Sure. So this root name server will send back an NS response. And that's basically saying, I don't know, but you should ask this name server over here. And then it will also send back a DS response, which is essentially saying, this key is authorized to sign for, this subdomain. And then it will send back an RRSIG for this DS and an RRSIG for this NS response as well, just so that everything is signed. Now, these RSIGs are signed by some key. And in the case of the root name server, how would the local name server know what these keys should be?
So if they signed it with the private key and they had a public key, then they can use, the local server could use the public key.
Okay, but how does the local server know what the public key of the root name server is?
It either has to ask someone they trust or they just have it hard coded.
Yeah, usually for the root name server, these keys will be hard coded because it's kind of like the root certification authorities. We just kind of have all of their public keys hard coded into our devices because we need some, root of trust. So after we get these, then we start going to, say, this .com name server. And then this will send back another name server response, as well as a DS and another RRSIG over the DS and an RRSIG over the NS. Now, these signatures, well, maybe for the .com, I'm actually not sure. They might be hard-coded as well, just because .com is such a common domain. But let's just assume that the local name server doesn't know .com's DNS keys off the top of his head. Off the top of its memory. I believe, and this, I can't remember, I think this is correct. Don't quote me on this though. I believe this will also send back a DNS key response, basically saying this is the public key that I will be signing with.
Mm-hmm.
And this will match up with this DS record here.
Okay.
So your local name server can verify, okay, I've gotten this DNS key from this name server. Yeah, I've gotten this DNS key from this name server, and I can verify that this DS response from the level 1 up in the hierarchy matches this DNS key. And once I verified this key, then I can use this public key to verify the signatures for this NS and DS response. And then it just, recurses down through there. Does that answer your question?
Yeah, so it's all like dependent on the local server first having some hard-coded key that they trust.
Yeah, because it's hard to be able to trust anything if there's no one you trust to begin with. Because if you're completely isolated from the world and you have no root of trust, there's no way you can somehow create trust. You can only assume, you can only extend trust from something you already know is trusted. It's kind of generally true for most systems.
And then I don't think this isn't on like within scope of the syllabus, but like, so if an attacker were to like tamper with your local name server so that the certificate is like the keys that you have hard coded, like they change it, then everything would just break.
Yeah, if the local name server is compromised, then you can't trust this local name server anymore. Let's turn it red just to say it's evil. And at this point, actually, you don't even need to go through all of this DNSSEC stuff, because if you remember, the responses from the local name server aren't usually signed. So this here is entirely unverified, because usually it's on your local network. So at this point, the attacker could just send a false response and poison your cache. This is why in the last discussion section we were saying every one of these devices here can still poison Alice's cache. It's only when it's outside of the internet where everything's secured with DNSSEC that you can't, that a non-path attacker can't poison her cache anymore.
Okay. That makes sense. Thank you.
I guess I'll see you on Monday?
Yeah.
Cool. All right.
Thank you.
See you.
Bye.